So we're talking about partial derivatives. And if you remember, we talked about dy dx giving us a rate of change of y with respect to x, right? Dy dx gives the rate of change of y with respect to x. That's in our notes from a long time ago. So we're taking a step back, returning to derivatives, and now we're actually going to talk about derivatives and how they're found for multivariable functions. So partial derivatives are derivatives found for multivariable functions. If you remember talking about the related rate problems, and one of the examples I think we had was if I just throw a ball across the room, if I'm just tossing it across the room, we could track that ball in terms of its horizontal distance, and then its vertical, and that changes with respect to time, right? So we actually had a multivariable function. The functions that we're going to see, and actually let me put a little thing here, these multivariable functions, what that means, it's a function with more than one independent variable. So let's write that down first. It's a function with more than one independent variable. So not exactly like the with respect to time problems, but we've seen something similar in that sense. And you'll see these written as z equals, and then we use the notation f, but it's a function of x and y. So z equals f of x comma y. And that's where x and y are independent variables. Okay, so the functions we look at, they're called z. We can write them as f of x comma y. And we're going to take derivatives of these multivariable functions. And so let's define what a partial derivative is. So there are really going to be four kinds. Let's break it down from the beginning. You might want to put a little heading that says a partial derivative of f, and then drop down a line, and put a little bullet point. You'll have the first case where you're taking a partial derivative of f with respect to x, you can write it is the derivative of f obtained by treating x as a variable and y is a constant. So we're working with these multivariable functions. We'll call them z, or f of x, y. X and y are independent variables. But if you see it says take a partial derivative of f with respect to x, you treat x as the variable and y as a constant. You already know how to do that. It's just going to be the notation and then actually remembering some of the rules from the beginning of the semester. So then the next little bullet point you could put will be, we're going to do it with respect to y. And you could probably fill in the rest of it. It's the derivative of f obtained by treating y as the variable and then x as a constant. Okay, so we have referenced above how we used to talk about derivatives. We used to have dy dx. Remember what another way we've been using to denote a derivative? F prime. We've been using the prime symbol, right? Okay, since we're now talking about a multivariable function, we no longer use prime. We have a different way to show it. We use something called del, or we use like f with little subscripts. So just some different ways that you'll see it. Notation. You have this f and then a subscript x. That's going to indicate the partial derivative of f with respect to x. So if you actually want to go up and put that next to where you have your definition, that's fine. So you could do the same thing where you're talking about the partial derivative of f with respect to y. You'll also see this del. It's kind of goofy. It's called a del. Del z over del x. It's the partial derivative of that function z with respect to x. And these are called del. You could see it written as z and then the subscript x, or you'll see del f over del x. So all of these things are saying the partial derivative of the function z equals f of xy with respect to x. So I'll write that down. All right, so let's take a look at how we're actually going to use this. So let's say that we have a function z, which we can denote as f of xy. And I'm going to go ahead and put another equal sign here. It's equal to 4x squared plus 5y squared minus 5. And what you'll see is a function given to you like this, a multivariable function, and there'll be a notation. It'll ask you maybe del z over del x. And then you'll have to go, oh, what does that mean? It means take the partial derivative of the function with respect to x. So what do I do with the y in that case? What did we just write down? Treat it as a constant. Okay, so I move through this function. This is not too complicated. I use my basic rules of differentiation. What's the derivative of 4x squared if I'm keeping x as the variable? It's 8x, okay? I move along to plus 5y squared, but y is treated as a constant. Derivative of the constant is 0. Yeah, so I treat this as a constant, right? It says treat x as a variable and y as a constant. So this actually is my answer. That's it. Okay, let's do another one. let's actually just do the partial of z with respect to y. So two things you really have to get down. One is reading the notation, and then two, making sure you treat that other variable as a constant. So if I look at this function and I treat which one as a constant now? X. Okay, what's the derivative of 4x squared? It's 0 because x is treated as a constant. I move down 10y, and then I move down to the derivative of -5, 0. So this is actually quite easy as long as you read the notation correctly and then you understand that you have to keep the other variable as a constant. But this gets more tricky, as you can imagine. But it's still, it's not a bad concept because you've spent nearly the whole semester finding derivatives. Okay, let's look at the function f of xy. It's 7x squared y plus 3x to the 4th y to the 6th minus 6y plus 5x plus 4. Okay, let's say I'm asking you to find f and then the subscript x of xy. So I'm saying the partial derivative of f with respect to x. Okay, so you move through and you say I'm going to treat x as a variable, y as a constant. So as I go from left to right, what will you have? 14x. What happens to the y? It's a constant. So what do you do with constants when you take a derivative? I've always said they go along for the ride, right? It's going to stay there. Okay, good. So I've got 14xy. Yep, treating x as a variable, 12x cubed, y to the 6th. It's a constant. Okay, now what? Move down to -6y. What's the derivative of that?
0.
0, good, because this is treated as a constant. Okay, now plus 5, because x is the variable. Okay, so any questions on that? It's kind of awkward and weird at first because like I'm not supposed to do that. I used to have to do product rule or something. But you're talking about a multivariable function. Okay, these are partial derivatives. Remember that notation is going to tip you off, and you have to make sure that you're really paying attention to what it's asking. We'll have some more partial derivatives in a moment. Let's do the same thing, but now we'll take the partial of f with respect to y. Okay, so kind of walk me through term by term. Looking at 7x squared y, partial derivative of that with respect to y. Good, 7x squared. Does everyone see that? The derivative of y to the first is just going to be 1, and the rest of that's a constant. Okay, move to the next piece. Okay, so you multiplied, you took the derivative of y to the 6th, so you would multiply the constant, or excuse me, make the 6 of exponent, 6 times 3, 18, keep the x to the 4th because it's a constant, reduce that power by 1. Is that right? Okay, what about the next term? -6, anything else? Nope, we got it. Okay, good. As you can imagine, we could say find the partial derivative of the function, so we're still going to keep using this one for a moment. Find the partial derivative of f with respect to x, but perhaps we say evaluate it at 3, -1. So it tells you, I could have just started off with giving you the part in black where it says here's the function, and then I just say find the partial of f with respect to x, evaluate it at 3, -1. In that case, you would have had to do part A anyway, but all I'm asking you to do is plug in, right? So I go back to part A where I found that partial derivative of f with respect to x, and now I'm going to plug in everywhere there's an x, I'll plug in 3, and everywhere there's a y, I'll plug in -1. So I'm going to put a little note above this so I can show where I'm plugging things in. Right, so everywhere there's an x, you're putting in the value 3. Everywhere there's a y, you're putting in a -1. So what is 14 times -3?
42.
Okay, so -42. Then I've got 12 times 27.
324.
And then plus 5. So what does it come out to be? 287? Okay, and that's the answer that we want. Let's try another function. F of x, y, let's make it 3 times e, which is raised to, and this is on the exponent, 4x squared minus 6y. It's kind of a good spot in this semester to come back to talk about derivatives. It's been a while since you've taken a derivative. We've focused on antiderivatives. The first thing I want to ask is for you to find the partial of f with respect to x. So I'm going to treat x like the variable and y as a constant. So tell me a little bit about taking the derivative of an exponential. What kind of rule do I have to use here? It's chain rule. Okay, so what happens to this 3? Goes along for the ride. What do we do with the exponential? We rewrite it. And you multiply by the derivative of that exponent here. And remember that we're keeping x as the variable and y as a constant. So with that in mind, what's the derivative of that exponent?
8x.
Just 8x, isn't it? Okay, and we could make this simplified a little bit nicer. You can multiply the 3 and the 8x. This is 24x e raised to the 4x squared minus 6y. Okay, the same thing now for the partial of f with respect to y. The 3 hangs out, we rewrite the exponential, and what do we multiply by? Is it positive 6, negative 6? Negative 6, right? The derivative of negative 6y is going to be negative 6. Okay, so do we have any questions on that? Okay, let's try another one. So we're warming back up to our derivative rules. I'm going to draw a line here. We're going to find the partial derivatives with respect to x and respect to y. And then we're going to evaluate the partial of x, f with respect to x at the point -1, 2. So I'm going to give you a few minutes to start on this. Okay, so we've got x squared minus y squared all over y to the 5th plus x squared. Can you guys tell me what rule you're going to use? Quotient rule, and it has been a while. Okay, so we've gotten this nice answer here. We found the partial derivative of f with respect to x. I could actually ask you on the same problem, but I wouldn't for this particular one. I could ask you to go further. I could say find the second order partial derivative. And the way that that would look, so these are second order partial derivatives. The way that would look would be you would see two subscripts. So I'm writing f and then two subscripts x. That's saying find the second order partial derivative of f with respect to x twice is really what it's saying. There's also, as you can imagine, with respect to y twice. I could take the partial derivative with respect to x and then to y. So now I've got the subscript xy. Or I can write it as take the partial derivative with respect to f, with respect to y, and then x. So it's like taking a second derivative, and the only thing that you really need to note is like these last two, you read it from left to right. So let me scroll up because there's a few people that can't see back here. What this is saying is that you're going to find the partial of f with respect to x, then find the partial derivative of that with respect to y. So it's like taking a second derivative, but the order that's written really matters. So it'll make sense once you see an example. So I really have 4 of these things that I can do. So we're going to find all second order partial derivatives that means I'm talking about all 4 of those that are written above. My function is f of xy is equal to the natural log of the absolute value of 4x plus y. And that maybe all it says is find all second order partial derivatives. So how many do you have? There's 4. Okay. So I really want to find maybe an order. I really want to find the second order partial derivative with respect to x here twice. So what do you have to do first? You have to find the first partial derivative with respect to x. Okay, so if I look at my function and I want to take the partial derivative of this function with respect to x, what do you do? It's been a while since we did logs. 1 over the argument times the derivative of the argument, but now I'm using what is the variable? X. So the derivative of that is 4. Okay. Have I found a second order partial derivative yet? No. There will be an easier way than having to do quotient rule, by the way. So what's another way to rewrite this? 4 times the quantity 4x plus y raised to the negative 1. Okay. So I'm going to change color here because now I actually can find the second order partial derivative. Right? So I'm now going to look at this and take the derivative of that with respect to x. So the 4 is going to hang out, right? What do you do next? Bring that negative 1 to the front. It's chain rule, isn't it? rewrite the 4x plus y. What do I do with the power? Subtract it 1. And then what do you multiply by? Derivative of the inside, which we're talking about x being the variable, so 4. Okay, so I can rewrite this as negative 16 times the quantity 4xy, or 4x, excuse me, plus y to the negative 2. You guys agree with that? Okay. So I found my first one. Let's go ahead and find f, partial derivative of f with respect to x, then y. Because I've done part of the work, right? So I really need you to be able to see this notation. You go from left to right. You're first going to find the partial of f with respect to x. Do we have that?
Yes.
Okay, so I'll say we have the partial of f with respect to x. We wrote it as 4 times the quantity 4x plus y to the negative 1. The notation says now I'm going to take the partial of that with respect to y. So I'm looking at my partial of f with respect to x. I'm going to take the derivative, but I'm going to treat y as the variable and x as a constant. Okay, so tell me what to do. Keep the 4. Pull down the negative 1. Oh, I didn't write that. Okay. Subtract the power. Multiply by the derivative of the inside with respect to y, which is 1. Okay, good. So we've got negative 4 times the quantity 4x plus y to the negative 2. Perfect. Okay, so now I have my second partial derivative. We already, whoops. Let's find the second order partial derivative of f with respect to y. So what do I need to do first? Yeah, find the first partial derivative with respect to y. So my function's way up here. I take the derivative of this. What is it going to be? 1 over the argument times the derivative of the argument, which is the derivative of y is going to be 1. That's right. 4x is a constant. Okay, so do I have to write anything more? No. What's another way to write this, though? 4x plus y raised to the negative 1. Okay. Everyone good on that? Okay. So what we really want to get to, I'm going to take the derivative of that with respect to y. So what's the derivative of that going to be? Negative 1 plus times 4x plus y raised to the negative 2, and multiply by the derivative of the inside, where y is the variable, times 1. Okay, so we got another one. What else do we have? We've got one more, right? We can finish it. Okay. All right, how do I go from here? It says I start off looking at the first order partial derivative with respect to y. I've got that, and then take the derivative of that with respect to x. You guys see where we are? Okay, so what do I write down? Okay, so I'm going to use chain rule, right? I'm going to bring the negative 1 to the front. We're talking about right here. Rewrite the quantity, subtract 1 from the power, and multiply by the derivative of the inside where x is now the variable. Okay. And so I think we have our 4 partial derivatives. You guys agree? Okay, good.